Today, I will talk about protein structure, which is not only a textbook story but a lifetime story of Dr. Robert Hoover. When I was a PhD student, it was just after 3 or 4 years later when he received his own Nobel Prize. He was invited to have a lecture at Seoul National University. And at that time, his title like this, Protein Crystallography, not structure. Protein Crystallography at the interface of physics, chemistry, and biology. But the structure itself, protein structure itself, requires some understanding about physics in terms of its energetic consideration, also chemistry in terms of nature of chemical bonding, also biology in terms of its variety of functions, which we are interested in. You may not be interested in physics, chemistry, but you may be interested in biology, which may give you some profit or reward. Anyway, benefit. And yesterday, fortunately, I attended his lecture, which was held at Mogam Research Institute, of which mother company is Green Cross, which is famous for its antibody and drug manufacture. Anyway, as I told you, he got his Nobel Prize in 1988 at his age of 51. I'd like to put your perspective in very personal manner. Considering his age of 51, he was quite energetic at that time, but in terms of profit he made as a Nobel Prize winner, like this, prize share 1/3. What it means, total prize money at that time, I don't know exact, but nowadays around $100 million. It may be quite big, but let me continue. But anyway, nowadays billionaire is very rich, but billionaire is not rich according to Korean standard. Even $1 million, we may not buy an apartment in Seoul. Not general, but some specific area, downtown or expensive area. Anyway, at age 62, he co-founded a company named Proteus, which is specialized in the service of structural biology, simply protein crystallography. He didn't know very much about NMR or electron microscopy, but mostly protein crystallography he did a lot. And around that time, he visited our institute, CRIC, and he made several lectures through few years because he was connected to World Class Institute, which is within our own institute in Ochang campus. And as the webpage said, 1999 he founded, and he founded another company, Supremol. Recently it was sold out at the price of, let me find, where is the price? Here, $200 million, approximately $225 million. So yesterday I was told about the story of his own daughter. Actually, he had 3 daughters and 1 son, 4 children anyway, and among them, 3 did major in economics, not in science. The rest one, now she's a teacher in history. And among them, I don't know which one is which, but Papa, she said, Papa, now I'm proud of you. She didn't say anything at the time of his Nobel Prize, but at the time of now your research is worth of $200 million US. So Anyway, this is about the story of his business. So I'd like to take your interest or attention not only in textbook story but also about some business story, which is the success of Robert Hoover. As a scientist, Arnie is saying he earned one-third of $1 million, but as a founder of some business like this company, he earned more than 100 times larger. So not only be limited in science, but have a perspective in business, especially when you are trying to learn protein structure or simply biology. Biology has much impact than other science because it directly involves human life. Also, human quality of human living, like food and some cosmetics, everything are related in biology. Okay, that is one perspective I'd like to share with you. And he was very proud of this company. And I myself has carry a plan to follow his footsteps. I'm not at age of 51, so I have promised. I have a dream about Nobel Prize as he did. Let's be ambitious. Boys and girls, be ambitious. But even Nobel Prize doesn't bring us a lot of money, so we may be interested in his business story too. Anyway, biology has much impact than any other science because life is much more precious than any other resources. Losing life, nothing. But having life in good health condition matters a lot, especially when we are becoming older, also when we have more wealth. When we are in poor condition, we may sacrifice something, we may sacrifice ourselves for something, but when we have something in our wealth, we would like to sacrifice money for our living, or simply spend money for better life, or better living quality. That is even happening in China. China, when they are poor in national standard, they didn't afford very much about cosmetics. But now, Chinese rich people in China come to Korea and they buy lots of things. Girls may know about that. And that is part of the story. And let me go through hard story too. Last time we studied introduction of crystallography from the perspective of language, not as a science. I'd like to continue that perspective too, not as a hard science like mathematics and physics, but soft science, much more softer than biology itself, language, like literature, as you said, Muhammad. But we are not doing literature, but we are doing science with language. So crystallography is hard in the sense of its use of mathematics and some physical principles, but it can be soft because its contents are very few. Main concepts are very few. Let me continue main concept. Also, before jumping into main concept, today, on top of such a crystallographic concept, you will learn about molecular parameters. That's whole story about protein structure in mathematical and physical sense. Molecular parameters, that is the keyword you will take as a second example. And with such a molecular parameters, also with the story of Robert Hoover, I'd like to bring you to develop your own interest about protein structures. In this chapter, also my talk may involve some perspective about variety of proteins, not just structure, variety of proteins. DNAs and RNAs are rather simple than proteins, but proteins are much more complex in terms of length, in terms of complexity. It can be huge in size, and it can be very complex in terms of its organization. So you may have your own interest, like antibody or drug target, or even some materials for cosmetics, or some basic ingredient for food, like sweet proteins, which Dayan is studying now. So in parallel to molecular parameters, you may be asked to develop your own interest. Okay. So that is part one. Which interest do you develop, or did you develop after learning about Robert Hoover's experience? There will be open question to you. Today you may have some scratch idea, but further you may develop your own idea. So you should have your own interest. Then you will make much better progress with your reading. That is my hope and wishes. And as I told you, very few ideas. Electron density as a symbol, rho XYZ, and position parameters XYZ, and lattice parameters ABC in capital. And structure factor is a related parameters or related data, FHKL. But problem is they are all in symbols. So not in this chapter, but later chapters, we will learn how to decode such as symbols. But symbols are very limited in crystallography. This whole, nothing else. Okay, that is important. No others. But I will not explain this. But I would like to remind you, we have very few key concepts in crystallography. To reveal such data, we need to do some crystallographic experiment. Then we will determine the protein structures, and that is the topic of today's lecture. Okay? And Fourier transform I'll skip, but from this, I'd like to remind you, normally especially in information technology, also electrocommunication, they are talking about Fourier transform as a function of time. But as I remind you, we in crystallography, we are talking about Fourier transform in space. Now, figure one. What do you think in terms of three protein structures? Actually, presentation of three protein structures. What is major differences between these three?
Different in size and different in molecular weight.
Yes, molecular weight. Given you figured out these are molecular weights. 8 kilodalton, 150 kilodalton, and even 2 megadalton. Mega and kilo, 1,000 times different. Even we have several megadalton structures, different in weight. So, different in size, different weight, different volume, so different size in length. Okay? Around 30 angstrom, 100 angstrom, and 150 angstrom. But why do we have more differences in weight than in length? Length, this one, roughly 4 times. But why do we have 1,000 times in mass?
Because of overlapping.
Because the length depends on the molecules, but this weight depends on the how many molecules are attached and how much complicated.
But I remind you, only one molecule here, one molecule here, one molecule there.
Here is there are many kinds of protein together. Here.
Single protein here, single protein, single protein, single protein.
Okay. And this is the difference in the tertiary structure, quaternary structure, and secondary structure.
All are in tertiary structures as a monomer. It may not be true, but let's suppose all are in monomeric structure. Here, simply monomeric, we are seeing one alpha helix together with two beta sheet. Here, as you said, we have several alpha helixes and several beta sheet composed with tertiary structure. But first one is still tertiary structure composed of alpha and beta, not just a single secondary structure, because it is made of alpha and two betas. This does not require your biological thinking, but this requires your physical thinking. So simply, based on this length scale is like this. Let's suppose 10 angstrom, order of 10 angstrom, and order of 100 angstrom. Okay. So anyway, we are filling some structure or some object into this dimension and this dimension in terms of length, but in terms of box, not length. This box will be like this, and this box will be like this. Then, if we multiply 10 by 10 times, that is 100, right? So if multiply 10 times 10 times 10, result in 1,000. So only increase in 10 times in length will result in increase in 1,000 times in volume.
Yeah.
So length scale, volume scale are not the same. Volumes increase in length tripled in volume. Does it make sense? So here, I would like to remind one thing. Fourier transform usually as a function of time, but as I told you, crystal Fourier transform as a function of space. But the space, what I meant is usually in terms of ABC, length scale. So ABC, so-called A equal, B equal, C equal, some angstrom is a unit of length, angstrom. But if we increase in ABC 10 times, it will result in 1,000 times in volume. So, so you need to connect this kind of volume changes as well as length changes, because protein structures, simply protein is in 3 dimensions, not in 1 dimension. So you should have an idea of 3 dimensions. Okay, space as a length perspective, also space as a volume perspective. You need to develop volume perspective. Here, if you consider length scale increment in this way, you may expect volume scale or weight scale. Weight is proportional to volume when we have equal density. Roughly, we have the density of protein around 1.2 gram per cubic centimeter. So, regardless of type of proteins or protein entities, we may have similar weight or similar volume depending on molecular weight. So I took 1 BPI, for example, because that is the simplest one anyway. I don't want to show you this kind or this kind, but this kind, let's have a look at this from PDB data bank. Did you have chance to open PDB website?
Like I've opened, but
After last time. And
yeah.
Not yet?
Not yet.
Then after this time, please try to go through website, a PDB website as your pleasure or kind of hobby. Then you'll have better chance to develop your own interest in potentially rewarding business. And PDB, each month it has a month of structure of month, protein of month. I don't. Molecule of month. Molecule of the month.
Of the month.
Yeah. Molecule of month or of the month. So this is kind of highlighted structure reported in that month or this month. So not only your proteins, you are not working on protein, you are working on proteomics.
Yeah.
So you are dealing with many proteins at one time. So when you run 2D gel, actually you have several, even more than 100 or 1,000 proteins at one time. So by identifying each protein spot, you may characterize some protein on the spot or on the gel. Then you may have some publication about such a listing or proteomics result. Then you'll go through protein list, and you may have some interesting proteins among many spots. Okay. Then, and fortunately, or you may have structure solved or deposited in PDB. Then you can link structure with potential impact on your study. That can be possible pathway for profitable research. The reason why you study proteomics may be to find some target protein for some cure or for some medical application, either as a cure or as a diagnosis. So most of the molecule of the month may provide some hint, like reading some digest magazine. Let me jump this in. From last time, we talked about PDB data statistics. At the year of 84, I found 155 cumulative number of protein structure deposited at that time, and 20 of that year. Among them, I found bovine. Let me talk about one BPI. I jumped a lot. Sorry. This one BPI. I found this is bovine pancreatic trypsin inhibitor. After reading particular PDB, you can jump to PDB and you can type this code name, PDB code name. It revealed bovine pancreatic trypsin inhibitor, and I put those keywords into PDB back again, and I found several, more than 100. Among them, oldest one is like this. B5PTI, deposited in year 1984. It was solved by two persons. One of them is Robert Hoover. So also it was done by not only by X-ray crystal but neutron crystallography, neutron and X-ray together. It's called joint refinement, and it contains only 58 amino acids. It was crystallized in several crystal forms. This one is crystal form 2, and what I'm showing here is crystal unicell parameters ABC in angstrom in different ways. Particularly 5 PTI, 1 BPI, almost same, but at different temperature 6-PTI, completely different. They are not in the same crystal form. So this is showing 1-BPI is listed in PDB, and this was done in 96, and this was crystallized in P271, 2727 space group. I'll explain how you read space group symbol, but anyway, let me continue and here. Let me continue. Anyway, BPI is simple protein here among PDB. Molecular, not only molecular month, here variety kinds of proteins are presented. In terms of size, this one huge, and we have more bigger one, and photosynthetic center is in several megadalton, and viral coat proteins in another megadalton, and among them you can find some categories. So you may develop your own interest group in terms of protein categories. Robert Huber, he did develop his own interest in kinase. Here I didn't list them, but if you read protease and supramol group, firstly he developed his interest in kinase and proteases, and he made some protein gallery product. Actually, they made several hundred proteins ready for crystallization and ready for small molecule drug screening. So they are providing such a protein as a service. Then he developed his specialties in antibody, here Fc gamma receptor for antibody therapeutics, and he sold out such a company for big pharma like Baxter. So among PDB structures, you may find something interesting to you, and you can have your own study which is specific to such a protein category, like drug target or some biomaterial and some sweetener, and yours is fluorescent proteins. Okay, that is first part I'd like to share with you. And how about having some break? Okay. Let me talk about Nobel Prize winners, women Nobel Prize winners in chemistry 2009. She is Ada Jonas for the studies of ribozyme structure. Then recently we have Nobel Prize in chemistry winner in 2012 for the studies of GPCR proteins, G protein coupled receptors. So 2008, you may remember 2008 Nobel Prize in chemistry. GFP. It's not about structure itself, but GFP, one third, Rosa Tizen. He did a lot in terms of protein crystallography and protein engineering for GFP proteins. So only counting from year 2008, GFP and its structures, 2009, ribozyme structures, Ada Jonas, woman scientist at that time, and 2012, GPCL, It's all in chemistry. So protein structure is not directly of biological problems, but directly of chemistry. So you need to learn something about chemistry. Okay, then let me talk about chemistry. Chemistry is about bonding. What is bonding to you?
Connect.
A connection
Connection.
of what?
Atom. Two atoms.
Atoms, right? Here, for proteins, we have peptide bond. So carbon alpha and carbon backbone, and carbon backbone to nitrogen backbone, and nitrogen to carbonyl. This carbon, same or different? Here, simply mistake, I think. Textbook. What about your own textbook there? I will show you another mistake later. But I found textbook was okay for the matter. Is that okay? Still long. What about yours? Some editions are revised and correct.
Page number. Page.
All are wrong.
How is
So,
correct?
hmm?
How is correct?
You have hint here.
Yeah.
CO. It should be CO,
Oh.
not NC. CN, CN, C, 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 C. Here, just here, not only
Oxygen.
atomic symbol, but also positional symbol like alpha, beta, gamma. Side chain atoms have more designation. Secondary, primary carbon, secondary carbon, tertiary carbon in terms of order of connection. And here you should have some sharp eyes to catch others' error, not to repeat such an error in your own lecture. That is the quality of PhD scientist. So you should exercise your own authority to correct this kind of mistakes. If you repeat others' mistake, that's the quality of undergraduate. Okay. Anyway, here you correctly pointed that bonds are between atoms. So that is all about chemistry. Previously we talked about space and weight. That's about physics. Physics does not talk about bonding, although material physicists are talking about bonding too. But that's kind of exceptional. Physics law doesn't explain anything about bonding, but chemistry law is trying to give us understanding about such a bonding, so-called chemical bonding. So bonding between atoms are important for chemistry. So as a structure, simply protein structure, we need to understand the chemical nature of each bond, like a CC, CN, CO. That is major bond. On top of that, we have something else, something more. Depending on each amino acid, we have some extra. Okay, but mainly as a peptide bond, we have 3 major bonds. Okay, also it leads to hydrogen bonding too. What's the difference between peptide bond and hydrogen bond in terms of its nature? here for each peptide bond, also hydrogen bondings are listed.
It's longer than peptide bond.
Longer.
Bonds.
In terms of symbol, these are in straight line.
Weak bonds.
In terms of presentation, yes, weak.
These
Yeah.
are intermolecular and that is intramolecular.
It's very interestingly wrong answers. But I highly regard your boldness. Also, it's very interesting points. Intra and intermolecular. Okay, it's very important. Muhammad intentionally made some wrong answers for us. Anyway, this is about physics, space, and length scale and volume scale. Okay, you should keep this mind. Angstrom and triple angstrom. Now, let me talk about chemical bonding and. How simple it is in terms of physics. In terms of physics, we talked about only length and volume, no more right now. For crystallography, actually, only for crystallography, we are not dealing with time. We are only dealing with space. Simplified physics. Also, even crystallography itself doesn't involve any physical consideration of energy or spectrum. I'll not talk about energy and spectrum today. But in terms of scattering, we have two kinds of scattering: elastic scattering and inelastic scattering. Elastic means no loss of energy. Inelastic means loss of energy or change of some energy state. Crystallography, we are dealing with scattering, elastic scattering alone. So we are not considering some energy changes during experiment. So we are using very simplified physics. Only space concern. Only space matters. No energy, no time. Only space. Physics law are described in space and time and energy and momentum and its motion. But crystallography, we are not dealing with motion. Actually, we are dealing with motion in terms of in some disguised manner, not direct manner. It's called atomic displacement parameters, or simply displacement from the center of average position. But anyway, have your focus on space alone, nothing else in crystallography. Now biology, now chemistry. What did you say about hydrogen bonding? I forgot your word.
Oh, that is intramolecular bonding.
Intramolecular.
Oh, sorry, intermolecular.
No difference in terms of your wrong answers. Thank you very much. Inter and intra. Molecular. But making wrong questions, wrong answers, and being corrected is the way we can learn in significant manner to have deeper understanding than before. If you stay at the margin or surface, you cannot make any progress. But if you make some mistakes in this manner and being corrected, you have deeper understanding than before. Anyway, Muhammad brought us these two words, intermolecular and intramolecular. That is the point he can distinguish between peptide bond and hydrogen bonding. But first of all, interestingly, he made the same mistake last year. I taught something about this. So this is second mistake. So you will have correct understanding from today, from now on. Interestingly, protein can be very huge. So for simple molecule like a single peptide or just dipeptide, it cannot form any intramolecular bonding between those atoms, but proteins can be very huge. Even for BPTI, it was made of just 58 amino acid, of which molecular weight is just 8 kilodalton. It forms at least one alpha helices and more than 2 beta sheet, and every alpha helices have intramolecular hydrogen bonding. I'll not talk about intramolecular hydrogen bonding in alpha helices in detail, but please read the textbook, Muhammad, especially for you. If you read section about alpha helices, there should be description about intramolecular hydrogen bonding within alpha helices. Alpha helix, a single alpha helix can contain several intramolecular hydrogen bonding. Without them, it cannot be formed into alpha helix. So, by having specific intramolecular hydrogen bonding pattern, it can be either alpha helix or beta sheet. So, secondary structure have specific intramolecular hydrogen bonding. Okay. Also, this one is not even intramolecular bonding. Muhammad did try to distinguish peptide bond and hydrogen bond with the help of this terminology, inter and intramolecular bonding. He thought hydrogen bonding can be intermolecular bonding and peptide bonding can be intramolecular bonding. In some sense, he is correct. In terms of peptide bonds can be intramolecular bonding. But to be technically correct, intramolecular bonding or hydrogen bonding is reserved for hydrogen bonding, not for this kind of peptide bond, because this is more like not intramolecular, it's more like interatomic, simply bond. As a intramolecular bonding, we are bond is already bond between atoms, so this is already implied. So what I'm saying is intermolecular, intramolecular, and interatomic. I'd like to bring these three words to be specific. So all bonds are interatomic bonds, first of all. But some bonds are either intermolecular or intramolecular. In terms of protein, between proteins more than 2, or simply 2 proteins, bonding, hydrogen bonding between 2 proteins can be intermolecular hydrogen bonding. But hydrogen bonding within a single protein can be intramolecular hydrogen bonding. So hydrogen bonding have 2 kinds in terms of involvement of proteins. Self-protein, intramolecular. Other protein or same kind proteins but dimer or tetramer, multimer, intermolecular. Is that okay now?
Yeah, okay.
But you brought very good answers, but wrong. But interatomic. Here, I'd like to remind my own question. Which molecular parameters do you know about protein structure, primitive and derivative? I didn't explain anything yet about primitive and derivative, but I'll give you answers in advance. We are talking about derivative parameters now. Primitive, derivative. This is not word written in textbook, but I intentionally brought these distinctions between parameters we'd like to talk about. Derivative. Primitive, what does this mean? Primitive. Oh, that is good word. Simple and good word. Original one. Primitive is original. Original data. Or original. Derivative is not original, right? In terms of source. This is source and this is kind of transformed or calculated one. So derivative parameters are calculated parameters based on primitive parameters or data. So if you measure distance in this way, any length or distance, what's the difference between length and distance? Let me erase this. This book is using length, but some other literature use distance, both in angstrom. What is length and what is distance in terms of its application or nuance?
Length can be like the length of a bond, and distance can be like distance between two molecules or something.
Two atoms.
Two atoms. So distance is what did we say? Comparative kind of.
This is kind of open question. I'm trying to get your authoritative explanation. We should exercise our own authority as a PhD scientist. This is not a wrong or correct questions, but you made some good point. Comparative and what is between atoms. And first of all, I'll provide my own version, but you may follow me or you can develop your own version. As Saba said, length has more connection with bond, but distance can be general. If we have two atoms, like any atom C and any atom another C at different residue, let's say this in residue 1, this is in residue 12 or something else, not adjacent one. Even adjacent one in peptide bond, where do we have? Here, this one C, this one N, adjacent one. This is bond length. Distance between C and N can be regarded as bond length. But what about this distance, C1 and C2? They are not directly connected. Then distance between C1 and C2 can be called distance, but not bond distance or bond length. So specifically, bond length is reserved for such between connected atoms. But distance can be calculated anyway between any two atoms. So distance is length. Length not in the sense of bond length, length between any two atoms. you can calculate anyway. But length coupled with bond is the distance between connected atoms. So bond length and bond distance can be used all together when they are connected with each other, each atoms. But distance is not specifically for connected atoms. Distance can be more general. Length can be more specific with the word of bond attached to in front of length. Bond length, bond distance are interchangeable, but bond length is more specific in terms of bonding nature. But distance as a single word is more general in terms of computation. Both are valid, but we have some slight differences in terms of application. Okay. Any distance itself can be calculated from position. If we have two atoms, we have position from each atom. Here, position of C1, if you know, and if we know position of C2, we can calculate distance between these two atoms. So we need to know two atoms to calculate distance. But what about angle? Now I'm shifting to angle. Here, this book doesn't explain anything about angle, but the author used bond angle. Roughly saying this is 120. If you have some cross contact here, it can be less than 120, but if it is planar, it can be larger than 120 or close to 180. Like aromatic ring, anyway, we are close to 120. Anyway, to calculate bond angle, we need three atoms. If they are connected, it can be called bond angle. Unless it is connected, simply angle. Okay. And hydrogen bonding, here do we have, sorry. Oh, hydrogen bonding. Here did I have hydrogen bonding? Ah, here. Hydrogen bonding, not only distance in dotted manner, but also we have angular component. Angle between oxygen, hydrogen, oxygen, and hydrogen, oxygen, hydrogen, so-called donor angle and acceptor angle. Okay? Hydrogen donor side and hydrogen acceptor side. So we have angle between three atoms. We have distance between two atoms. But what about four atoms? What do we have for four atoms? Can you speak louder?
It would be rotation.
Cross to rotation, but we have some technical word for such a rotation. Torsion. Yeah, right. But like length and distance, we have another word for torsion. Torsion. What is that? In later chapters, we studied about dihedral. Do you remember? Dihedral. Interestingly, we have only angle. Angle. I'm sorry. Let me erase whole. Level 1. With one atoms, what do you have in terms of information, geometric parameters?
Ladder.
Huh?
Just one.
Two, distance, length. 3, angle between three atoms. and dihedral. Let me summarize in this way. Firstly, we should have position in space. Sorry, AC. Position x, y, z in space. And if you have two positions or two atoms in space, we can calculate. I said calculate or compute distance. But if they are connected, it can be called bond length or bond distance. Also, we can calculate angles between three atoms anyway. But if they are connected, they are close to 120 for some sp3 geometry. sp3 geometry is about chemistry, chemical bonding. Or 180 for triple bond or some double bond. Okay? Not double bond, triple bond. Angle is just bond angle. And here, who can explain the difference between dihedral angle and torsion angle and simply angle? Dihedral angle, torsion angle, and bond angle. You talked about torsion angle. How did you know that? Did you read textbook or did you have some prior knowledge about torsion?
From textbook.
You read textbook.
Torsion is the length between four atoms.
Yes, angle between, angle is not, we cannot say angle between four atoms. Angle between three atoms makes sense. If you have 3 points, 1, 2, 3, then this way, angle between 3 atoms. Distance 1, 2, distance between 1, 2. Angle 1, 2, 3, then angle from the center of 2, we can define the other atoms 1, 3, then we have angle between 3 atoms. But angle between 4 atoms are not defined. It cannot be defined in the same way of bond angle. Bond angle is defined by this interaxial angle. X, I said axis. Axis can be defined 2 point, 1, 2. Here, 1, 2, one axis, 2, 3, the other axis. Two axes can define angle between two vectors. That is mathematical, but we cannot define dihedral angle in this manner. There is explanation in the textbook how we can define dihedral angle or torsion angle, but let me talk about dihedral as English word, not as a mathematical definition. What does this mean, di? Two. Wow. Now you are recovering your strength. So, kind of restoration, refresh. So, I is 2, and what is hedral or hedron?
Water. Water.
Pace. Polyhedral or polyhedron. You have some cubic. Cubic has 6 faces, right? Cubic. Yeah. Cubic has 6 faces. It's kind of polyhedron. Regular polyhedron. Cubic is regular polyhedron. Same face, exactly. So-called polyhedron. like this, we have dihedral. This means of two faces, or planes. Okay? Plane, of two planes. So if you read textbook, dihedral angles are defined by two planes, not two axes. Angles are defined by two axes. Dihedral angles are defined by two planes. But in the textbook, in later chapters, they also use dihedral angles. But like bond distance and bond length, these two words are interchangeable. Torsion angles and dihedral angles are interchangeable. But dihedral, the word dihedral has more connection with geometry. Torsion has more connection with which subject?
Rotation.
Rotation. That's the word that Doim said. But torsion has some energetic term and physics term.
Angular.
Yes. It has involvement with angle and rotation. If you have some rotation, but it's not a free rotation. I'm trying to invoke or demand your common understanding of English word of torsion. When do we have? Oh yes.
Twist.
Yeah. When we twist something, if it requires energy or force, we are experiencing torsion. Okay? Dihedral doesn't have any meaning in energy, but torsion has a meaning of force or energy involved in physics. So this is not free from physics. This is free from physics. Dihedral is purely mathematical. Torsion already word itself contains meaning of energy restriction. Torsion angle is not free. It is limited in energy consideration. Without having such a concept, you cannot go through alpha helix, beta sheet, and Ramachandran plot. I'll not try to explain everything behind Ramachandran plot, but you should have some key concept to attack or to decode the meaning of Ramachandran plot in protein structure. Also, as Muhammad kindly made mistakes for us, you should have sense of intramolecular hydrogen bonding. Otherwise, you cannot understand alpha helix. Otherwise, you cannot understand beta sheet in terms of the significant role of hydrogen bonding in alpha, beta secondary structures. Because of that, we have some restrictions or some preference in terms of torsion angle, in terms of dihedral angle. But dihedral angle free in energy consideration, but torsion angle is not free. It has some favorable reason and it has some not very probable reason. Favorable means energetically favored. Not probable means energetically crash or energetically high. So we should go for lower or stable position. Unstable or demanding position should be replaced into or transformed into lower state in energy or favorable. That is the main concept of protein conformation. Also, it also can be used as a validation tool. Once you determine the structure, either it can be correct or it can be wrong. How can you find wrong? Is like this. If the structure in very improbable torsion angles, possibly it cannot be correct. Okay. this is backbone torsion angle distributions. Here, with the word of torsion, here, energetically prepared. Okay. Also, even they used higher torsional energies. They connect torsional, adjective torsional with energies. So by changing torsion angles, either we can increase energies or decrease energies. That's the experience you explained. By applying some rotation around bond, actually dihedral or torsion angles are defined in the way of rotation, as you said. But it's rotation about this way. If we have atoms 1, 2, 3, 4, here axis, single axis, here double axis, here main axis around 2 extra axes. So this is rotation axis. 1, 2, and 4, 3 will be rotated with respect to 2, 3 main axis. So in terms of number of atoms involved, position requires 1 atom in space. Distance or length requires 3 atoms in space. And angle needs 3 atoms, 3 positions in space. And dihedral and torsion requires 4 atoms in space. And here, 1 axis is enough. So it can be called axial distance. Okay. Axial means of axis, distance of axis. And angle is the angle between two axes. Axis of 1, 2, axis defined 2, 3. Angle between two vectors or two axes. Dihedral angles are angle around. This is not between. Dihedral angles around. Major axis 2, 3 defined by 1, 2, and 4, 3. So in terms of rotation, what you are looking at is this is so-called Newman projection in chemistry. If we looking at through 1, 2, 3 overlap together, here 2, 3 overlap together, then we have 1 and we have 4, and this is angle between 1 and 4. This is so-called Newman projection. Newman projection in chemistry, stereochemistry. Anyway, distance, angle, dihedral angles are important parameters in chemistry, but position itself are not parameters for chemistry. Chemists are not interested in position itself. Position of single atom meaningless, no meaning to chemist. Only positions of two atoms have meaning, either bonding or non-bonding. If they are close enough to form some connection or some strength, then bonding. Likewise, angle, dihedral angles are meaningful for chemists in terms of stereochemistry, but no barrier. So which one is primitive parameters and which are derivatives? That will be your answer to second question. You will write down later. Okay. Anyway, any question about this?
So we can say position is the parameter of physics.
That is my articulation. It was not said or it was not written in that manner in the textbook. Textbook doesn't distinguish anything from physics, chemistry, biology, but intentionally to help your understanding, I made some articulation or exaggeration to distinguish origin of each terminology. Okay? Some terminologies are interchangeable, but I made some artificial distinctions between distance and length in terms of its connectivity or bond. Also, position, distance, angle, dihedral angles, respectively. Okay. That is my aid or help, HELP, for you to follow textbook. I'd like to encourage you to develop some habit like this. Language awareness. Like people have their own nationality and authenticity or origin of bloodline. Even you and I do not have same bloodline. Even morphology may not be the same. Muhammad and I do not share surface color. I'm talking about face color. Even hairstyles are not the same. Okay? Eyes colors are not the same. So we have different ethnic origin. Likewise, each vocabulary may not have same origin. Science is not the science. Science, we have some specific fields. So I'd like to help in this manner to equip you with strength in vocabulary or terminology. Now you should be able to distinguish molecular parameters, at least 3 kinds: distance, angle, dihedral angles, as described in textbook, and I pointed out position as primary one or primitive one. But let me continue primary one in terms of PDB file. Have you ever looked at PDB file? Even you didn't check any PDB yet. How about you? But you never looked at PDB. So it's worth to look at PDB together. Okay. Then let me open one PDB, unless you have any further questions. Let me continue later. Anyway, let me show you these 2 views. One is textual, like this. Here, atom number 1, 2, 3, 4, 5, 6. Here, amino acid residue number. Residue number 1 is arginine. Residue number 2 is protein. And bovine pancreatic trypsin inhibitor contains although it's very small proteins than others, in figure 1 contains more than 500 atoms already, not including hydrogen. Don't forget, this doesn't contain hydrogen. 58 residues and non-hydrogen atoms, 460 atoms. This is a single molecule or single protein which contains 58 amino acids and 460 atoms, non-hydrogen atoms. And the other view, graphical view, here we have same model but in different presentation. This contains alpha helix, here beta sheet, 2 beta sheet, small fragment alpha helix, But each amino acid are displayed in stick models, but all in atomic models. But if you hide this cartoon model, these atomic models, but if you hide tick and showing only cartoon, we are losing atomic details. We are just looking at models at alpha and beta and random cores, secondary structure level. With this model, we cannot compute distances or any accurate measure of hydrogen bonding. So likewise, we can look at opposite direction, more detailed ones, subatomic models, which are not atoms at all, subatomic particles. But to describe biological functions, it's good to stay in atomic model. So let me come back here. 좀 그러네. 치고 다시 할까? Kind of your memory test or test of your understanding. I'm sorry to repeat this again, but for you it's more beneficial. Now everything is erased. And we talked about crystallographic data. And parameters. All are numbers. And what distinguishes data and parameter?
Experiment.
Muhammad said experiment. So data, experiment gives you data. But what gives you model? Experiment gives you data, but what gives you parameters?
Model.
Oh, yes. I made a mistake. I gave you answers, so you are perplexed. Model. Model gives parameter. What kind of parameters do you have from atomic model? Let's talk about primitive one first.
Position and space.
Position in space. Yes, position always in space in primitive way, but which position? Whose position? Or atoms. Yeah. Of atoms means atomic. Atomic position in space. Then what can we have?
Length of the bond.
Bond length. So we are not saying atomic length, because atomic length is meaningless. Single atom doesn't have any meaning with length. Two atoms will have meaning, and it will become bond length if they are connected or they are close to each other, which can be regarded as bond. So bond length. If we have three atoms, we can talk about angle. And if they are connected with bond and bond angle. And fourthly, we have dihedral or torsion. In the textbook, it's called torsion angles. So all are parameters from atomic model. So here, scattering experiment or diffraction experiment and atomic model. So if you have something in front of experiment, either it can be called diffraction or scattering. If you add something in front of model, it can be called molecular or atomic. So our title of this coursework is Biomolecular Crystallography, molecular or atomic. In front of model, both may be fine, but we are not saying molecular positions because we are dealing with each position of each atoms. Molecular position either be, it may be center of mass of total molecules, but single atoms has single position in space. So these become molecular or atomic model. This is diffraction or scattering experiment. And 잠깐 pause 주실래요? What did I talk about? Data and parameter. I forgot something. Why did? Anyway, I'd like to remind you natural science always involve data and parameter. So for you, I'm encouraging you to have a habit to distinguish these two kinds of numbers, data and parameters. They are numbers, but they are not the same from the perspective of experimental perspective or modeling perspective. Model, as you said, what is the nature of model?
Understandable.
Yes, more understandable or simply understandable. Understandable. Then, if I use your vocabulary in this side, experiment can be undertakeable. This is my invention. Why? I'll explain why I use the undertakeable. This is not dictionary word. I invented this word for you to have some symmetry between understandable and undertakeable with these two activity. Experiment is our activity, but modeling should be another activity. Purpose of research is not just data collection. If you studied research planning and what is the full title of the name? I forgot.
Practical research planning and design.
Research planning and practical research
planning and design.
Planning and design. Thank you so much. Just data collection or research is not research because it doesn't provide any further modeling. I said it was not written in the textbook. In my own vocabulary, I am trying to help you in terms of distinguishing data and parameter under the light of experimental side and modeling side. In later chapters of this book, great emphasis was put in terms of modeling, structural modeling. But not only in crystallography, but also in science in general, even philosophy. You are doing Master of Science level or Doctor of Philosophy level, so you need to develop some understanding about our undertaking. Our undertaking is like this. We are doing experiment not just because your professor asked you to do. That should not be your explanation. You should have your own understanding about why you are doing experiment. You are doing experiment either to verify your model or to improve your model. In crystallography, you are not asked to develop new atomic model. Models are well developed in terms of physics. You are not asked to do some physics experiment. Such an experiment was done in early 20th century, mainly done by Bragg and Bragg, father and son physicist team. I talked about carbon structure, diamond structure, and graphite structure. Both are composed of carbon atoms alone. Graphite, what color do we have for graphite crystals? Black. What color do you have for diamond?
White or transparent?
Transparent. It was tricky, but no color, transparent, but shiny, because it reflects light so well and very shiny. So jewelry, expensive one. Bragg and Bragg, as a physicist, they developed atomic model of crystal structures. So we are not required to develop such a physical model, but we are doing protein crystallography to develop not physical model, but which model? In terms of number one, physics. I said not physics, but anyway, physics. Number two, chemistry. Number three, biology. In which area are you trying to understand your protein, if you are interested in some protein?
Chemistry. I am interested in biology.
Biology.
Yeah. Function. But
Function of protein structure is the realm of biology. I tell you why not chemistry. Chemistry actually is the essence of atomic modeling, not only of diffraction scattering experiment, but also its connectivity. Whole connectivity described in terms of bond length and bond angle, dihedral angles are realm or area of applied chemistry. But biology is more than that. Chemical models are about connectivity. But as Muhammad pointed out, in terms of inter and intramolecular bonding, proteins usually much more complex than other small molecule in chemistry. I'm saying chemical compound in synthesis. Because of that, we have much more flexibility in terms of its building principle. Secondary structure already complex than any other chemical compound. Upon such a secondary structure, we are building tertiary structure as a single protein or single monomer. Then using such a monomeric unit, we may build quaternary structure, which may contain several monomers inside of functional cells. So our concern is not to build physical model nor chemical model. We are trying to build biological model with the help of atomic position. Once we know atomic position, we can calculate all bond length, bond angle, torsion, which is the area of chemistry. But our answer is not only in bond length, bond angle, torsion, but beyond that, in terms of its complexity or in terms of its point of application. Our point of application is not just adjust bond length. Bond length is almost fixed once atom types are assigned, either carbon or oxygen. Once carbon, oxygen given, we have almost constant or fixed range of bond distance. But what is the parameters are we expecting most variations or great variations among these three? bond length and bond angle torsion. Torsion. Mostly bond length is close to 1 point some angstrom. Bond angle close to 120 degree. But torsion angle varying between minus 180 to plus 180. In between we have 0. That's the nature of Ramachandran plot. But it's not randomly or evenly populated. Some regions are highly populated and alpha helix. The other regions beta helix, beta shape. Even alpha helix can be either left-handed or right-handed. They are not the same. Okay. In such a way, we have great variation in torsion. And this has something with secondary structure directly, alpha, beta, even random cores, and composing those secondary structures, we can build tertiary and quaternary. So secondary structures may be interest of chemistry, but tertiary and quaternary are not the interest of chemistry directly. We can say it's a part of biochemistry, but biochemistry is already part of biology. Biochemistry, biochemical model is not chemistry model. This is model of biology. So we have some level of understandings. So physical model, very primitive in terms of design of experiment at the early days of X-ray diffraction. But now we have some fixed model in terms of physics. We are not trying to invent something else rather than atoms. We will specifically using atomic model, nothing else. What do you know about anything else regardless of atoms? In terms of particle names, atoms are particles. What do you know about any other thing in physics? Other particles in physics?
Electrons, protons.
Oh yes, electrons and protons, and we have quark. Q-U-A-R-K. Even within nucleus, nuclei, any nuclei, inside of nuclei we have some subatomic. We will not talk about this. Don't be confused. This is enough for chemistry, and we should aim to know more complex things behind protein structure. That's the biological model. Biological models are created using such a building block in physics and chemistry, and in terms of complexity, physical model, most simple one, atomic one, and chemistry model, peptide bond level, and biological model, even up to quaternary model. So with the knowledge of position, we can go through whole up to biological model. So your role is to determine structure with the help of physical, biochemical knowledge to know biological function in terms of structure. If you change structure, the protein may act different way, and you may have better function or changed function. That's the whole purpose for biotechnology venture, as Dr. Robert Hoover created. Okay? You may be interested in your own business in biotech, and you may be concerned about your biological model. Done? Question? What do you have in your tongue then? Why are you hesitating to say something?
I would like to ask about experiment and model. What is the first? Because when we have when we need to plan research, we need to assume what is model we follow, and and then we do experiment, and we got data.
Data.
Yeah, data. And I'm confused. What we need to, when we planning research, what we need to assume we can get final result. I mean, final result, parameter or data.
You have some point which is relevant to my third question. So now, with the knowledge of data and parameter under the light of experiment model, I will specifically answer your question. Okay. Actually, that's the way we should go, or we should finish today's lecture. Here, first of all, these are derived one: bond length, bond angle, torsion, and what secondary structure, tertiary structure, quaternary structure. All such derived parameters or model, biological model, can be computed or calculated based on atomic position information. So this is primitive atomic position in space. Okay. So anyway, these chemical interests can be answered with these physical parameters. Anyway, I should emphasize this again. These are not data. These are primitive physics parameters. Okay, these physics. Primary concern in physics is to determine atomic positions. Then bond information in chemistry. But in biology, we rarely talked about bond distance or bond length. In chemical journal, even we have table for bond information. But in biological journal, you never see such information or result as a form of table. Very rare. Rather than such tables, you may see figures like a ribbon diagram or cartoon diagram, right? That's the realm of biology. But anyway, with these physical parameters, you can derive chemical parameters as derived one, and biological parameters or biological conclusion based on this. So I will focus on this in terms of crystallographic data. Is that okay?
Yes.
But I will not erase this. I will only erase this part. Physics, chemistry, biology, in terms of level of complexity and in terms of its originality. Any physical parameters are original parameters just after model experiment conversion. And chemical one, secondary, and biological one, finally. And here, so understandable at the level of biology are not same as understandable at the level of physics. Physics is more like numbers in text, as I showed you. But biology is more like figures, as I showed you using pi more. But to have such a figures understandable for biologists, we should have numbers in text or computer file. Okay? But numbers. XYZ in angstrom. Not only numbers in angstrom, but also if you remember what I showed you in terms of PDB file, we had atom type, carbon, oxygen, nitrogen, etc. Such information should be included, not only position. There is huge difference between carbon and hydrogen in terms of its scattering factor or electron density simply. How many electrons do we have for hydrogen? 1. How many do you have for carbon? Yes, 6. Even heavy atoms like gold. Sometimes we are using gold for not for chemical bonding, but for gold and platinum for heavy atom derivatives for crystallographic paging. But I like to explain this. But anyway, we have some heavy atoms. Even sulfur is heavier than oxygen. Okay. So not only positions but also atomic type. Atomic type plus positions are part of model. So under the light of atomic model, our job as a structural biologist or protein crystallographer is to determine which atoms are which place. We should determine atom type and atom position together. But these are parameters, but how we can transform or calculate these parameters are from this, anyway, this combined together, this x, y, z. But here is some tricky point. If you write down rho x, y, z electron density, but if you write down atom type and x, y, z, these are not identical information, but equivalent information. What I mean by not identical but equivalent is in terms of figures. If you remember some previous figures, and these are in terms of numbers of functions this way, but these are in contouring. Contour is in ball and stick. Actually, ball in space. Stick can be rendered as a bond length, but balls in space can be regarded as atoms in space. Each ball can represent different atoms. Different color or different size can represent different atoms in figures. So numbers can be presented in figures, and in terms of figure representation, ball can be regarded as atoms, and contour can be regarded as electron density. But they are not identical in terms of presentation or in terms of model. These are more direct or explicit. These are kind of intermediate. Once we have experiment, here I brought back electron density. In crystallography, what is the opposite pair of electron density? I'm asking to remind us in terms of key concept or keyword. Oh, very nice. What HKL? HKL like XYZ. Oh, very nice. FHKL and XYZ. Okay. Electron density rho, but you can regard rho presenting atom type, and FHKL data, parameter data. You should have some matching in your mentality or your heart. HKL as a coordinate in data space, XYZ coordinate in parameter space, but what matters is atom, identity of atom in each space. Identity or magnitude, not just identity. Magnitude, or if you regard F as a complex number, any complex number itself in HKL coordinate. So we can transform FHKL directly to rho XYZ through which transformation?
Fourier transform.
Oh, very nice. Fourier transform. So these are equivalent in terms of information content. But here, what we really have is not atom type, just Fourier transformed image of FHKL. So we have some contouring, but still with electron density alone in terms of contouring presentation is not directly reveal atom type. So by looking at such a contouring information or electron density information, what I did try to show you is a good program which shows you electron density, but we are missing today. Next time I'll show you with electron density program. But anyway, just take this with you at PhD level, not undergraduate or just graduate level. Electron density is a transformed data of HKL. I said transformed data. One of you talked about transformation today. These are not parameter yet, transformed data, so-called intermediate. I told you intermediate. But from this kind of transformed data, this FHKL is not directly related to atomic model. But once transformed, these are comparable in terms of figures. We can overlap electron density contouring together with atomic model in ball and stick, especially ball, unless we know bond information. So we can fit atomic model inside of electron density. That is so-called fitting. Fitting between data and parameter through model. But this is not specific to crystallography. Actually, this is general to any kind of natural science in terms of model building and in terms of designing experiment. So this is common, but this is not well explained in any other textbook. Biology, physics, chemistry, it doesn't have this kind of explicit model building process or explicit experimental design process. But crystallography is very unique in terms of transforming the data and comparing such a transformed data against model, particularly in crystallography, atomic model. So Fourier transform of structure vector is a comparable image to atomic model. So we are seeing such a overlapped image. One is contouring image, the other is atomic image. Such a thing are well explained using 20 amino acids. If you look at the textbook chapter 2, you may see 20 amino acids rendered with electron density. It was not given just in ball and stick model. It was rendered with electron density. That is unique in crystallography. If you look at biochemist textbook, you will not see electron density rendering. But because of crystallographic nature of model fitting or model building, both images are presented. Transformed data as a Fourier transform FHKL, and our understanding of atom position in space with possible rendering of bond either in color or in stick. Okay. We are almost done. Any question in terms of data parameter distinction and in terms of experimental model building, experimental planning, model building, planning and building. And in terms of data, primitive data in experiment is like this, FHKL. and primitive parameters are atom type, XYZ. But still, we are missing something else in crystallographic experiment and crystallographic model building. What's that?
Unit cell ABC.
Oh, very nice. We cannot build HKL in space without having ABC information. Anyway, we need to know ABC. In reciprocal space, A star, B star, C star, and transformed data space, we have A, B, C. Both will be bases in each space. Here, so-called reciprocal space, and here real space. So we are doing experiment in reciprocal space, and we are building model in real space. They are connected in reciprocal manner. Length of A star is 1 of A in orthorhombic. I will not explain orthorhombic today, but you will see what orthorhombic means.
Rhombic shape.
A rhombic is shape, yeah. Also means orthogonal to each other. Very correct. But you can take this like frequency. Frequency f is 1 over t, right? T is period in space. A is period in time. Period in time, and A is period in space. Likewise, we are dealing crystals in three-dimensional space. So we have the other two, B and C, like Y and Z. So we have three orthogonal cases. Then A star equals 1 of B, and B star equals to 1 of B, and C star equals to 1 of C. So if you have periodicity along X, Y, Z in terms of ABC period in space, then we will have reciprocal numbers in diffraction space or scattering space. That's all you need in terms of this Fourier transform. Then with given data, you can compute this. Actually, you are not computing this for yourself. Computer will do. So you will just click, or you will just initiate some computer software, and it will be transformed, and it will display some contouring image in graphics, and you are just looking at the images, and you can put your atoms based on your sequence. Which sequence? Protein sequence. Yes, correct. Protein sequence. Fortunately, proteins are almost following their amino acid sequence sequentially because of the nature of peptide bond. So for secondary structures, once we are given with sequences, we can trace them. Trace. Atom by atom according to amino acid. If you have some features looking like alpha helices, you can put amino acid along such a helices. If you have some flat atomic arrangement, then you can put beta sheet. Also, as we started with hydrogen bonding, you can confirm such a feasibility with possible hydrogen bonding among such a neighboring amino acid. Still intramolecular hydrogen bonding. With such a intramolecular hydrogen bonding, alpha helices or beta sheets can be stabilized energy consideration. That's all you need to know about X-ray crystallography for protein structure. Now, can you answer the rest question for yourself?